All right, so in these notes, I'm just going to show you the steps for writing a two-column proof in order to show that two triangles are congruent. Okay, so here are the steps. We'll do a few examples on this page and on the next page. But the idea is when you're writing a proof, most likely you're going to have a diagram that goes along with it. And so before you kind of come up with your plan, you always just mark the given. All right, so label your diagram with everything that you know. And make sure to mark, because these are common, you're going to mark any vertical angles. And you're going to mark any shared sides or angles. Right, that's the reflexive part of things. Okay, once everything's labeled, and these are kind of for more basic proofs, but once everything's labeled, you can usually choose the method that you're going to use, the criteria that you're going to use, whether it's going to be side, angle, side, 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 hypotenuse, leg, angle, angle, side, or angle, side, angle. Right? There's 5 ways that we're going to show that two triangles are congruent. Angle, angle, angle is not a method, and neither is side, side, angle. Right? Unless we know that the second leg is longer than the first leg. Okay? Now, when we write our proof, we're going to write the steps of our proof in the order of the method that we choose. Right? So you want to keep everything in order so it's easy to follow that we're proving a pair of corresponding angles and another pair and then a side. Okay, so we're going to fill in the reasons using definitions. This is what goes in the right-hand column. Definitions, properties, theorems, or postulates. Okay, so we're going to disprove, in this case, we're given that P is the midpoint of AB and of CD, and then we're going to prove that triangle APC is congruent to triangle BPD. All right, so we mark what's given, and the idea is P is the midpoint of AB, so we can mark that. And P is also the midpoint of CD. So we know, by definition, that's what midpoint means. It means that it divides that segment into 2 equal parts. Well, then the next step is, what else do we know that maybe wasn't given to us, but it's in the diagram? And in this case, we've got these vertical angles. And at this point, with these basic proofs, a lot of times the method kind of jumps out. You can see that we have a pair of corresponding sides, an included angle, and another pair of corresponding sides. So we're going to use side, angle, side. When we write our statements, we're going to write them in that order, but in this case, to use side, angle, side, we had to know that this was the midpoint first. So we're going to say our first statement is what was given. P is the midpoint of AB and CD. And that was just given to us. Okay, now that we know that P is in the middle, we know that these pairs of corresponding sides are congruent. So now we can start listing things in this side, angle, side order. So AP, or side AP, is congruent to side BP. And the reason we know that those two are congruent is because we were told that's at midpoint. So by definition of midpoint. Okay, so we've used the sides. Now we need to go to the angle. Angle APC is congruent to angle BPD. In that case, we know that those two angles are congruent by the vertical angle theorem. Okay, so we've got the side, the angle. Now this last side, CP, is congruent to DP. And again, we know that those two we marked them congruent because we knew this was the midpoint. So by definition, the midpoint, we know that to be true as well. All right, so we have all this information kind of in order. Well, we can now reach a conclusion. You don't have to write this, but these three dots in a triangle mean therefore. So kind of all this. Therefore, here's our conclusion that triangle APC is congruent to triangle BPD by the side angle side method. We'll put a little box there to say that our proof is done. All right, so on this page, I just wanted to list some of the common properties that you're going to use in these proofs. Reflexive, we've already seen quite a bit. Reflexive, we're going to use that when the triangles share a side or an angle. So something like this where they have a shared side. Or maybe you've got two triangles like that both share an angle. All right, definition of midpoint. That results in two segments being congruent. Vertical angles. All right, we know angles that look like this, that are formed by two lines intersecting at one point. Well, they can only do that. Definition of angle bisector results in two angles being congruent. Right, and so you might have something that looks like this, and you're told that this is an angle bisector. So then you can mark that these two angles are congruent. Okay, a reason that we can or a statement that we can put in our reason column is that right angles are always congruent. So we're going to use this when you're given a right triangle and or a square or rectangle. So something that may look kind of like this, draw a right triangle. And then from this vertex, draw another right triangle that ends at the other vertex. Well, how do we know these two angles are congruent? Because all right angles are congruent. Okay, 8, definition of a perpendicular bisector. Right, this just results in two segments and a right angle. Right, so maybe you're told that this is a perpendicular bisector. Well, therefore you know it's perpendicular and it bisects. Again, everything that comes after the number is something you're going to put in the reason column, or at least it's potentially something you can put there. The alternate interior angle theorem is a common one. Right, use when you're given two lines that are parallel. So if you have a diagram with parallel lines, look for alternate interior angles. A lot of times you might see something that kind of looks like a parallelogram that's been divided into two equal parts, or just divided down the middle, and we have parallel lines. Well, that forms alternate interior angles in two triangles. Okay, a new one that we've discussed, I guess we just haven't given it a name, is what's called the third angle theorem. And the third angle theorem says if you already know two angles in one triangle are congruent to two angles in another triangle, all right, so I'll let you draw that for a second. So you have two triangles. We know two angles in one are congruent to two corresponding angles in another. Well, the third angle theorem just says we know that the remaining angle in each triangle has to be the same. The third angle has to be the same. So that's the third angle theorem. All right, number 5, the definition of segment bisector. right? The definition of a segment bisector, that's going to result in two segments being congruent. Doesn't have to be a perpendicular bisector. That's why this is a little bit different. You know, you can have a segment, and then you can have a bisector that just splits it right down the middle. Doesn't have to be perpendicular, though. Okay, and then finally, just don't assume anything if it's not already given. You know, if it's not in the diagram, it's not given to you, don't assume it to be true that you just say, well, like in this, you know, maybe those two angles are congruent just because they appear to be. Well, if it doesn't tell you that, and the information doesn't tell you that, don't assume it. All right, so we'll do this one together. You do that one. All right, so given side AB is parallel to DE, I can mark that. And AC is congruent to EC. Well, that's already marked. We're going to prove that these two triangles are congruent. So what else can we mark? Well, we know that we have these vertical angles that are congruent. And given that these sides are parallel, then what we have is we actually have two pairs of alternate interior angles. But we know that angle A is congruent to angle E by the alternate interior angle theorem. And from there, it should kind of jump out at you that we've got two angles and an included side. So we can use the angle side angle method. Okay, and all that information kind of was started from the given information. So we're going to say AB is parallel to ED, and that's given. And because these lines are parallel, we know that these alternate interior angles A and E are congruent. So angle A is congruent to angle E. That's the alternate interior angle theorem. Right? We're listing everything in order. Angle, side, angle. So now we need to say side AC is congruent to side EC. That one was given. Okay, and then finally the last angle, the last pair. We can't just call it C, right? Because if we just say C, it's not clear which one we're referring to. So we use three letters. Angle ACB is congruent to angle ECD. That's the vertical angle theorem. That's our reason. Okay, so we have an angle, a side, and an angle. So therefore, we know that triangle ABC is congruent to triangle EDC by ASA. All right, you do this one. When you come to class, I'll just check that you have it done. But you should have, just because I left 5 spaces doesn't always mean it's going to be 5 steps. But in this case, you should be filling up all 5 spaces. All right, so that's it. I'll see you in class.